So let us continue our discussion on quantum statistics. So from this video onwards, we are going to start learning about Fermi-Dirac statistics. So as you all know that in quantum statistics we had briefly introduced about two statistics. So one we have discussed in the previous few videos, that is Bose-Einstein statistics. So now on we will learn about this Fermi-Dirac statistics, which mainly deals with the fermions. So we have talked about what fermions are. So fermions are those quantum particles whose spin has got odd number of h cross by 2, right? So the odd integer values of spin, I mean like odd multiples of h cross by 2, their spin quantum number is that. Okay, so in this video we aim to learn about Fermi-Dirac distribution law, right? How every statistics we started learning about their distribution law. Then we will talk about Fermi-Dirac distribution function. Then we will talk about Fermi energy and then effect of temperature on Fermi distribution function, and then eventually Fermi temperature. So everything that you see, every line has got word Fermi. Okay, so then we also have introduction why name is associated with this, because Enrico Fermi was a person who started studying about this distribution of these fermions. Okay, this quantum particles which has got all the spin odd multiple of h cross by 2. Okay, so let's talk about Fermi-Dirac's distribution law to start with. Okay, so once again we'll go back to our consideration what we had initially, what we consider for starting of any distribution law that we discuss about. So here again let's consider a system of n independent and indistinguishable particles. So as from the last few videos onwards, when we started talking about quantum statistics, so we have been talking about these particles which are indistinguishable. Okay, meaning if you take two of them, you really can't differentiate between both of them. Okay, both look alike. All right, so then these particles which we're considering now, the n independent particles which are indistinguishable, these particles have definite energy and they occupy definite positions in space. So that means what, we can represent them by a phase point in the phase space. All right, so then to determine the energy distribution of these particles in statistical equilibrium, which we have been carrying out, right, for other distribution, what do we do? Whatever available volume we had, right, so we divide that into, let's say this is our available volume, right? Okay, so we divide that into many compartments, right? So and each of them represents what, some energy level or some interval of energy, and within that energy level we have quantum states, and which we represent in this scheme of things is that cells, right, which are of equal size. So again so let me just divide this, probably in some way we can just divide. Okay, so maybe this is one cell, this is not necessarily be like whatever your compartments could be. Okay, so your compartment, let's say this is 1, this is 2, this is 3, 4. So I should have joined this part. Okay, so 3, 5, like that. So I have a ith compartment, the last compartment let be k. Okay, so idea is what, I will have means I have a total of n number of particles, means n number of now fermions, right, which are to be distributed in this volume, which has got k number of compartments of unequal size. Okay, so and each compartment has got like cells, right, which are of equal size, small boxes are there, right? Okay, these cells are of equal size, and typically this number of cells are way larger than this compartment. Okay, I mean the number of cells. Okay, so meaning if you consider compartment, it will have a very large number of cells, or now to start with quantum states which we represent. Okay, so each of these box that you see here, as we have discussed in the previous distributions law as well while deriving that, so this represents a energy level, right? So it's a representation of the energy level with a mean energy. Let's say for the k compartment, this is mean energy of this compartment is ek. So we will be considering this ith compartment to start with. Okay, which has got mean energy ei, and particle are to be distributed ni in that. So how do I distribute ni fermions in this energy level? So idea is to N1 particle or N1 fermion to be distributed in compartment 1, N2 in compartment 2, or meaning the energy level 2. Okay. Similarly, in the ith, so Ni number of fermions are to be distributed in ith energy level, which is having mean energy Ei. Similarly, so on and so forth. If you keep going in the kth compartment, we will be having nk number of fermions to be distributed. Okay. So then this is our macro state. There are how many ways we can distribute this many fermions in this entire volume, right? That will give me number of microstate for that macro state. Okay, so here total number of fermions is n. So if I sum up the fermions in each of these compartments, or the energy level that it contains, I mean the fermions in each of these compartments or each of these energy level n1, n2, n3 all the way ni plus then nk, if some of them must give me n. Okay, so that is your total number of fermions. Okay, now these particles, these fermions are to be I mean they are governed by some laws, or I mean some conditions. Okay, so that's why I have some postulates. So these particles are indistinguishable, as we started with. So there is no distinction between the various ways in which Ni particles are to be chosen. Okay, so meaning if you have a collection of n particles, out of that for the ith energy state, or for the ith compartment that we are trying to consider here now, right? So I have to choose Ni out of that total of n fermions. Ni I will be choosing to put it inside this compartment I. Okay, so now this, even if you choose, so the different ways you can choose this Ni number of fermions from this collection of total number of n fermions. Okay, so you cannot really make any distinction. Why? Because any Ni number will give you the same thing, because the particles are indistinguishable. Okay, but this we had a different case in Bohl's meaning Maxwell-Boltzmann distribution law, right, where we are trying to derive or to learn about this distribution law regarding the classical statistics. Okay, so you can compare these two. So the second point is these particles, these fermions, okay, these quantum particles obey Pauli's exclusion principle, according to which we all know that there can be either no particle or only one particle in a state or in a given cell. So in each of these cells that we have seen here, right, it can, at the max, it can have only one particle, or there'll be no particle in that. So that really indicates, right, it's indicating that the number of cells must be way larger than the total number of particles, isn't it? Otherwise there will be no space to, I mean no vacant space for the occupancy of these particles, isn't it? Okay, so yeah, so that's what it means. So Gi, which represents the number of cells, okay, number of quantum states in their energy level I, must be much greater than Ni. Ni is the number of particles. Okay, now idea is what? I will consider this ith compartment or ith energy level, right, compartment, okay, and having mean energy Ei. So how many ways I can distribute this Ni number of particles in this Gi number of cells? That is our idea. That's how we have discussed all throughout our distribution laws. Okay, so where we were trying to derive that. Okay, so the total number of ways, different ways of arranging these Ni particles among Gi states or Gi cells is given by, so you have, let's say like this, you can consider, not necessarily it has to be a linear array, okay, how you have considered in the previous distribution law, I mean like while deriving for Bose-Einstein distribution law. You simply just take, there are Gi number of cells. Okay, since each cell meaning only one particle are allowed to sit inside in one of these cell, right, only one particle is allowed inside one cell, so there cannot be more than one particle inside these boxes or cells. Okay, so what will happen if I have Gi number of cells? Okay, so I take one out of that Ni, I take first particle, so I have Gi number of ways to distribute, because I can put here as well somewhere, any one of them I can put, so I have options of arranging it in Gi number of ways. Now okay, take the second particle, so because this one particle is already occupied, so the available state for me is Gi minus 1. So for second particle, I will have Gi minus 1 number of ways to arrange that particle, because I will have that many empty space or empty seats to sit there. Okay. Now take similar third particle. So 2 are already filled. How many states are available for me? Gi minus 2. Similarly, you keep going. Okay. So if you keep, so how many ways now I can arrange these Ni particles in the Gi number of cells or Gi number of states, because the Gi anyway we know this much greater than Ni. So that means what? I'll simply have a product of this, whatever for each one of these particle I have got, Gi into Gi minus 1. So I can have this. So this many ways I can arrange these Ni particles in Gi number of cells or Gi states, which will lead to me this Gi factorial, right? Gi factorial by Gi minus Ni factorial. Remember, this is the last term is Gi minus Ni minus 1. See, we started with its meaning here, see, right? Gi, so that's why it will end with Ni minus 1, not N. Okay. So I will have this many ways of arranging this Ni particle among the available Gi state. Okay. But the point is now, because these particles are indistinguishable, let's just consider like 3 states. So let's say I have all 3 of them are filled like this, let's say, for example. Even if I exchange this at this, will it give me a new state or new configuration? No, it's not going to give, because even if I exchange, it will remain as it is what was previously, isn't it? Because these particles are indistinguishable. That means what? But in this count that we have made, there are so many meaningless configurations. I mean, meaningless ways are also counted there, because if I exchange this any 2 of these particles, or maybe reshuffle the particles here and there, it's not going to give me a new different or distinguishable state or distinguishable configuration. So that's why similar meaningless configurations or meaningless ways to arrange these particles in this, you will get is Ni factorial number of ways are meaningless ways are counted in this. So a factor of this has to be, divided, okay, from this total arrangement. Okay, meaning what you have to keep in mind that, so there will be an Ni factorial number of ways you have to, there's a factor of this many will be meaningless configuration. So that you have to somehow take into account. So while doing so, you have to divide this actual count by Ni factorial. Okay, so this is your actual count for this, considering the fermions which are indistinguishable, that Wi gives you the number of different ways of arranging Ni particles in Gi cells. Okay, so this many is the actual count which will give you distinct ways of arranging these particles. Okay, so this is for ith compartment. Now you can generalize this for all the compartments, right? Isn't it? So you can generalize. So the first compartment will be this, second compartment will be this. Similarly, last compartment, the K compartment, you will get similar kind of ways. Okay, similar number of ways to arrange these many particles in their respective cells. So Gi represents a number of cells in for that particular the ith compartment. So Gk represents number of cells corresponding to the K compartment of K energy level. So now total number of ways to distribute N1 in first compartment or first energy level, N2 in the second, similarly N3 in the third, Ni in the ith, and then Nk in the K compartment. Okay, so that will be simply product of all these things, right? That's how we will get the number of microstates for this macro state, and this is given by this, and this is where it's written, you are familiar with by now. Okay, after getting the expression for macro, the thermodynamic probability, which is W here, right? So then what do you do for the statistical equilibrium? What do you have? The most probable macro state. How do you calculate? Which will have most number of micro state. Meaning what? And again we will use logarithm here, because W is a really large number, and you take first derivative of that, equate to 0, and then apply Lagrange method of undetermined multipliers, and you get all those things. Just follow what we have been doing for the last almost entire course, right? So you take simply log of both side. Okay, so you will get this expression. Then you apply Stirling approximation. What was that? So ln x factorial is given by x ln x then minus x. This you have used many times, so you know how to use this. So apply all these techniques that we have learned before. So while doing so, for each term you have to apply, right? So each term you have to apply the Stirling approximation. While doing so, you will get this from the first term, second term, then this is third term you will get. So, and in this process some things will get cancelled out. You will see that this minus g term will get cancelled out because in front you have plus. Similarly, your this plus n and minus n will get cancelled out, and you will remain with this expression. Then you take differentiation of this expression and d ln w, and then I don't think so I need to go through the differentiation part. This is as simple as you have been doing all throughout the course, right? That's the advantage of me, completing all those learnings earlier, and then we can use it simply. Okay, so and then I will have this, this will get cancelled out, this will get cancelled out, then you will see that there is a minus 1 here and then plus 1, so that will get cancelled. I'll remain with this term and only this term. Okay, so ln gi minus ni for that, and then minus ln ni. Okay, so this I have to equate it to 0, isn't it? Okay, so while equating 0, again let's ln a minus ln b, I can write ln a by b. So while doing so, then I can switch this numerator and denominator, so I will get this minus sign has appeared, right, because of this switching of numerator and denominator. Then this I multiply both side minus 1, so since right hand side is 0, it will be still 0, and then I will get this expression. Okay, so I will have this expression I will be using for Lagrange, this undetermined multipliers, okay, to solve this. Okay, and then we know that the system has to follow our two auxiliary conditions, which we have also seen in earlier distribution laws, right? First thing is a conservation of total number of particles, because this has to be constant, isn't it? And this was not followed in your photon gas. Okay, just to remind you. Okay, so since this n is constant, so dn will be equal to 0, and because sum of this dni over all the changes over all the states will be equal to 0. Dni means what? In the statistical equilibrium, in the equilibrium, what happened? There will be exchange of particles across the energy levels, isn't it? But overall change, if you sum them up, it will be equal to 0. So okay, and also the change is independent, which we'll be using, okay, across different states. Okay, then we have to use the condition that conservation total energies, same thing, the E is constant and dE will be equal to 0. All right. Okay, so what do we do now for our Lagrange method of undetermined multipliers? We multiply this by alpha, multiply with alpha, this with multiply by beta. Okay, and then add this one, this expression, this is 1 2, and then this is third one, isn't it? Add them up. Well, if I do so, I will get this expression here, right? So then I know that since dni is independent, because change in the first energy level is independent of what happens in the, let's say, 100 energy level, is independent. So that's why each of this coefficient has to be equal to 0. This we have used many times. Okay, and so that this term will be equal to 0, and that gives me reshuffling of left and right, and I will end up with this term, this equation. Similarly, you just keep going. Ultimately we will get the distribution function for, like Fermi-Dirac, or distribution function for fermions, which is called as Fermi-Dirac distribution. Okay, so I will have this as my, okay, so this represents number of fermions in the ith energy state or energy level, or in the ith compartment, given by Gi is the number of cells in that same compartment, and then e to the power alpha plus beta ei plus 1. See, in Bose-Einstein statistics we had this minus 1, not plus 1, right? And so you can generalize if you want to write. Okay, so meaning ni gi by e to the power alpha plus beta ei So if I just simply call this as some, let's say, what should I call? Let's say some eta. So this eta is 0 for MB, meaning the Maxwell-Boltzmann statistics. This is -1 for Bose-Einstein statistics, and is going to be +1 for this FD statistics or Fermi-Dirac statistics. Okay, just to give you a meaning a hint to remember how to. Okay, so all these three statistics, as you all know, in a classical limit, all will fall back to our Maxwell-Boltzmann statistics. Okay. All right. So let's So if you substitute for beta, you get, we know 1 by kt is our beta, so you get this expression. All right. So this is in our discrete, assuming your energy is discrete, right? So then we have to use for the continuous values. But before that, let's talk about Fermi-Dirac distribution function. This we have done for the Bose-Einstein distribution as well, right? Distribution function, which represents what? Meaning like how many ni by gi. That means how many numbers of particles are present on an average in each quantum state or each state. That's meaning. Okay. So since this is fermions now, so this is Fermi-Dirac statistics. Since there can be maximum of 1 particle per quantum states, so this function, distribution function f of ei, is a ratio of number of quantum states of energy ei occupied by electrons to the total number of quantum states available in the energy level ei. Same thing which I am trying to talk at just few seconds back. Okay, so therefore, so this fermion, this I have told you in one of the lectures, where that this represents the probability under equilibrium a quantum state of that energy is occupied by a particle or not. So this gives you a sense of the probabilistic behavior of the particle. Meaning this distribution function gives you a hint of probability whether the particle is likely to occupy that state or not. Okay, so this, nothing else, right? In this just function, you take this G2 down, then you get this distribution function. That's what it is here. Okay, and for continuous values of energy, okay, which we are going to use extensively, is given by this expression. Nothing else. Wherever ei was there, script e has been substituted. Okay, and for now to write in terms of the energy, the distribution law. So the Fermi-Dirac distribution law for energy range E and E plus dE, right? So here n of E dE represents what? A number of fermions which are present in the energy range E and E plus dE, where the G of E is the density of states, number of states available in the range E and E plus dE, and this is given by product of these two, distribution function and density of states function. Okay, isn't it? Or G of E. All right. So we are going to learn more on this distribution function. Okay, so that has a lot of implications in how fermions behave across different temperatures. We will try to plot as well. Okay, so now let's talk a little bit confusing as well as very important topic. Okay, this is Fermi-Dirac. This is Fermi energy. Okay, so now in case of, let's say now let's consider the temperature 0 Kelvin around that. Okay. In case of particles obeying FD statistics, meaning the fermions in thermal equilibrium at absolute 0, the energy levels from 0 to certain value, let's say, so you have n fermions, let's say, okay, n number of fermions are available, okay. So we know that, so let me draw this ground state with little different color, okay, and then you have lots of energy states, okay. Now, since each state can occupy only one particle, not more than that. So what will happen? Let's say there are n fermions. So then, depending upon the number of particles at 0 Kelvin or absolute 0, so what will happen? Particles will occupy like this, right? Isn't it? Only one is allowed. So all the particles will be filled up to a certain level, depending upon how many particles are available in the system. Then I can assign, or maybe, so I can assign a energy corresponding to this, whether the topmost field energy level, right? So I can assign an energy corresponding to that, and that is known as Fermi energy. So see, in case of fermions in thermal equilibrium at absolute zero, the energy level from 0 to certain value, let's say this EF, are occupied by particles and other energy levels above the empty, and the energy level above this dash line that you see, which is I'm drawing here Fermi energy, right? So then above there all are empty. Okay, and so this energy is known as the Fermi energy. Now see, Fermi energy is defined only at 0 Kelvin, whereas Fermi level, even though it is very colloquially used, Fermi energy, Fermi level, both are not same. Okay, so Fermi level is defined even at higher temperatures. Meaning what? Suppose let's say now I am absolute to 0 and I have defined this Fermi energy, right? So if I increase the temperature, what will happen? These particles or the electrons, let's say, or the fermions which were there in the lower state will try to go, right? It will occupy at a higher state because it has got enough kinetic energy to jump across, right? So means what? In that way, you cannot really define the highest occupied level, right? Okay. So that's why this Fermi energy concept at other than 0 temperature is not there. Okay, so Fermi energy, so for time being, just learn about Fermi energy. So Fermi energy defined only at absolute 0 temperature, and it is defined as the energy level, it corresponds to that energy where the fermions are, meaning the energy levels are filled up to that point, and above this energy level, there's no fermions or no particles are present, meaning all energy levels beyond this Fermi energy is empty at absolute 0. Okay, so we will come back to it again, okay, at some point of time. Alright, so according to this Fermi-Dirac statistics, the number of particles in the energy range is given by this, just we have seen here, right? This is right. Okay, so now for a system of electrons in volume V, so because we need to know this density of states, meaning the G of E, dE. See, we have this expression like G of P dP. Okay, now this Gs is a spin degeneration factor, which we have discussed in our earlier video. So Gs is nothing but twice S plus 1, and if it is particularly for electron that we are going to discuss now, so S is half. S is half, so Gs will be 2. Okay, so here 2 will come. So in place of 2 Gs, 2 will come for electrons. Now if we substitute what we have learned here, earlier, so P square is nothing but twice E, right? So from this is a classical expression of energy and the relation between energy and momentum, and P square, so dP we can calculate doing all these things, substituting back, I will get this G of E. So I'm not going to do it, okay? We have done it a couple of times in our earlier lectures. Okay, and then alpha in terms of Fermi energy is defined as like this, Fermi energy and then this chemical potential. Okay, I hope you all know what is chemical potential is. So we got expression for G of E, and then we also got alpha. Just substitute wherever they are, right? So you will get N of E dE, number of particles in that energy range, so number of fermions in the energy range E and E plus dE, given by 8 pi mv, V is the volume, and by h cube, h is the Planck constant, root over 2me, and this expression. So your alpha is minus, right? E to the power this is meaning minus of Fermi energy by kT, right? So that's why minus sign has come, and E is our energy, E. Okay, then plus 1. Okay, so and this is the distribution, the Fermi-Dirac distribution law for electron energies. So I said we are going to do it for electrons because I have substituted here Gs, right? This is S is half for electrons, so Gs is going to be 2. Okay, so substituting all those things, you got Fermi-Dirac distribution law for electrons. This expression, I mean N of E dE. Okay, so this is your expression for electron energy. All right, so the total number of electrons in the system now we can calculate using this, right? Because I know in that energy range how much electrons are present. So then how many how much of so what's the total number of electrons? Okay, so in that sense, so you have to integrate over 0 to Fermi energy, because all the states up to Fermi energy is filled, right? Whereas on top of that, all are empty. So we can count number of electrons in the system. And so putting t equal to 0, which is at absolute 0. So here you see, so I will remain on this. So how did I get this? So expression for this n of e is this. So here this part will come as it is. So from this term I will get 1. So that's why there is no expression of that. Okay. So I will remain with this e to the power. From here e to the power half will come. I have to integrate over that. So if I carry out the integration and substitute for these values that we have in the limits, right, I will get this. So this also you need to keep in mind. Okay. So this expression here, this I will be using for later, just few minutes to go. Okay. And then so we got an expression for Fermi energy in terms of this n. N is the number of particles, volume. Okay. And this remaining thing is mass of the fermions, and h is a Planck constant. Okay. So eventually we got this now total number of particles. Sorry, this expression for Fermi energy is given by this, which depends only on the density of the particles, not on the number or the volume. I mean, Fermi energy is independent of size and volume of the system, only depends on the number density. Okay, this is the expression for Fermi energy. This is one of the important expression that we aim to derive. Okay, so having discussed about Fermi energy, we need to calculate this average free energy, the average energy of the free electron. Okay, so average free electron energy at absolute 0 we need to calculate. But before that, we can have a momentum associated with the Fermi energy, which is known as Fermi momentum. Similarly, you will have energy temperature associated with the Fermi energy. You will be having Fermi temperature. We will talk about it later. Okay, so from this expression from the expression of this Fermi energy, we can calculate this momentum, Fermi momentum. Okay, so the Fermi momentum can be got nothing else, just simply substitute and reshuffle the term, you will get. Okay, nothing big deal to yes. So now we are in aim to calculate this average free electron energy at absolute 0. Okay, how do I get it? So this expression is important. So this I have got it from here. This I said. Okay, from here just reshuffle the term. So I knew I will be using this term which appears in our distribution law here, right? So this appears here, right? So I want to substitute for that in terms of Fermi energy. So that's why I got this is equal to this in terms of Fermi energy, and with the n is a number of fermions. So and I just simply meaning substituting this, I will get this expression. Okay, nothing else, substitution here. Okay, so now at absolute 0, I know that again E is EF. Okay, I mean you will see this term will become 1 automatically. Okay, okay, this should have been capital T. Okay, this should have been capital T. Okay, so I will have this, and then if E naught be the total energy of the electron gas at absolute 0. Let's say now the E naught is, so I have n number of in the system I have n number of electrons, and I have the total energy of the system is, let's say, E naught. Okay, so E naught I will get by this we have calculated earlier as well, to calculate the total number of meaning sum over, so we had done like this, dni is give me, or not exactly dni, ni actually sum, if I can. Okay, so ei ni, you have done this to calculate the total energy of the system. So here, but since we are using continuous values of energy, so I have to use integration and then substitute for the continuous values of the variable. Okay, so while doing so, again here, so n of E I have got from here, substitute just here. Okay, and this part we know that this part is going to be 1. So and I have a E front, so then from here e to the power half, so it will give me result e to the power 2 by e to the power 3 by 2. So then, and after integration I will get this. I don't think so I need to carry out this integration, as simple as that. Okay, so so there I think I have missed out the term. So this should have been f, because after substituting the limit you should get ef. Okay, and then I will remain with this. So this is the expression for total energy of the electron gas at absolute 0. Okay, so this I need to put it in a block. Okay, so this is the energy for the total energy of the electron gas at absolute 0. Now since I have n number of particles in that, so the average energy will be simply what, divided with whatever the total energy divided by the total number of particles in that. So I will get this expression. So this expression is typically asked in the exams, okay, to derive this average free electron energy at absolute 0. Okay, so having discussed all these things, let's talk about quickly the effect of temperature on Fermi distribution function. Okay, we all know what distribution function is, right? So there is n of E by G of E, and given by this expression. Okay, now at, let's say, very low temperature, let us consider like T equal to 0. And so before I start, let me just draw the function how it will look like. Okay, so I will have this, let's say this is your EF, Fermi energy, and this is x-axis for energy. Okay, and this is your f of E. So this function will look like this, something like this. Okay, and the condition here is that, so this will happen at T equal to 0. Okay, so now how do I get this? So if your T is equal to 0 and E is less than EF, meaning what, E minus EF is a less than 0, negative quantity. So the most important factor is this in this. So your e to the power, since T is 0, I will get a negative infinity. Means what? This is 1 by e to the power e to the power infinity, which is equal to 0. And so if I substitute 0 here, I will get 1. So the value of this function f of E for this condition will be equal to 1, isn't it? So this is the value of 1. So below this Fermi energy or EF, your occupancy function or the distribution function takes value 1. Whereas let's see what happens whenever temperature is very low, that is again at same T equal to 0, and this term is your energy is greater than EF. In that case, your this E minus EF term will be greater than 0. Okay, so if it is greater than 0, what will happen? Instead of this negative infinity, you will get a positive infinity. So for that case, so if you substitute here, so this is going to be even a very large number, and then if you substitute a very large number, and this f of E will be equal to 0. Okay, so that's why beyond this EF, your value of the function, the distribution function is 0. Okay, so at absolute 0, the value of f of E, that is the distribution function, takes value 1. So the probability of occupancy of the fermions at absolute 0 below the Fermi energy is 1. That means all the energy levels or energy states are filled up. Whereas energy above the Fermi energy, okay, energy level above the Fermi energy, all are empty, because your distribution function, which gives you the probability of occupancy of the particles in the quantum state, is 0. That's what we have discussed about while talking about the Fermi energy, right? Okay, so now let's talk about the any temperatures greater than 0. Okay, so in that case, what happens, again let me draw the plot. Okay, so this is your EF. Okay, so this axis your energy axis, this is your f of E. So here what will happen, let's say this is your 1. Okay, let me just, okay, so because now the temperature is, so here the function will look something like okay, so let me just zoom it up and clean a little bit, because it cannot be, okay, so this is a smooth function, okay, so you should not get confused by that. Okay, okay, so this is your, okay, so it will look a very smooth curve like that. Okay, so okay, so this is for your T greater than 0 Kelvin. Okay, so your plot will look, distribution function will look like this. Okay, so and the most important condition that we are going to learn, when your energy is equal to EF, so this term will be equal to 0, meaning e to the power 0, it will give you 1. So this will be 1, so your this value of this function will be half. So at this point, so this will be your half, this is 1, means what, above temperature greater than 0, Fermi level, now okay, Fermi level is that level which has got probability of occupancy of these fermions to be 50%, now half, that is your Fermi level. Okay, now I hope you get the point. Okay, Fermi energy is defined at absolute 0 and Fermi level is defined for any other temperatures. Okay, so and that level is the Fermi level is that level which has got occupancy always 50%. I mean, you can see it here, right? Your f of E, the distribution function value is half. Okay, so I hope you got the point regarding the effect of temperature on Fermi distribution. So if it is at T equal to 0, if it is below the Fermi energy, probability this distribution function is 1. Above the Fermi energy, this is 0. But whereas in case of temperatures greater than 0, as you will see, it will drop. I mean, it will have this kind of form that you have seen, and which will have which will take values greater than meaning this f of E will be greater than 0 if it is in energy, if it is greater than EF. So you can see from this for the temperatures greater than 0, and also it will be less than 1 whenever energy is EF, less than EF. Okay, so you will get this, and at exactly at E to the E equal to Fermi energy EF, then your value is half. Okay, so this is what we have learned about the dependence of, or the effect of temperature on Fermi distribution function. Okay, so the last point here to be learned is Fermi temperature. Okay, so as I said, while talking about Fermi momentum, we will have a Fermi temperature. So the I mean, here this T should not have been there. Okay, so this so ignore the T here, but T should not have been there simply. Okay, because how will we define, because your energy, so K EF is defined as K, so this is Boltzmann constant, so this is K and then TF. So the whatever the expression of Fermi energy we have, so in that you so TF will be given by EF by K. Okay, so simply what are the expression of Fermi energy we have obtained there, divided by K will give you the Fermi temperature. All right, now this temperature becomes again a scale for us, right? So if it is below the temperature below TF, which is your Fermi temperature, your distribution of the gas will be called as strongly degenerated, degenerate. And if the temperature it is just above the TF, then we will call it is weakly degenerate. And if it is very large, so your energy, the thermal energy is way larger than the Fermi energy, then we will call this non-degenerate. Okay, so we'll take up this degeneration, the effect of degeneracy on the Fermi gas from the next lecture. Okay, so we shall stop at this point. I hope you have got the points regarding the Fermi-Dirac distribution and distribution function, the Fermi-Dirac distribution functions, Fermi energy. I hope you go back and little bit contemplate on the concept of Fermi energy and Fermi level. Okay, and with these things I will stop at this point. Okay.